Good morning, dear students. My name is Ferhan Mazher, and today is 14th January 2022. Right now, I am with the 11 Cambridge class, and today we have set our hearts to solve an ATP paper. This is alternative to practical. We are doing Cambridge O levels physics, and we call this paper paper 4. And today we have selected October, November 2017 paper. So let's start this paper. This is 4-2 paper. This paper belongs from the zone 2, or we can call it variant 2. So let's start. So Cambridge International Examinations, Cambridge Ordinary Level Physics 5054, paper 4, alternative to practical, October, November 2017, 4-2 paper. The time allowed for this paper is 1 hour. Okay, so let's start. He says a student investigates the period of a simple pendulum. The period T is the time taken for one complete oscillation of the pendulum. She sets up the pendulum with its point of support, a fixed height above the surface of the bench. She does not change this height or the position of the clamp during the investigation. A scale diagram of her experiment setup is shown in the figure 1.1. So here we have that retort stand. Here we have that clamp, and this is the pendulum bob. This is the thread. Here it's supported from here. So the height of this clamp from the floor is D. The first question coming up, he says, measure the distance D on the figure 1.1 to the nearest millimeter. Record your results. Okay, so with the help of the scale, check what is this length, D. This is basically the height of this clamp from the floor. So with the help of the scale, you have to measure it, and the answer should be in the centimeters, and to the nearest millimeter, means point after point, 1 decimal place. So put a scale here and measure it. Figure 1.1 is drawn to a scale of 1/10 full size. Write down the actual height h of the point of support above the bench. So 1/10 means if something is 1 centimeter long on this diagram, in actual it is 10 centimeter long. So that's the scale, 1/10 full scale. That means something is 1 centimeter on this diagram. In actual, it will be 10 centimeter long. So here you have to tell the actual height. So whatever is the value here, just multiply it with the 10 and you will get that answer, and the unit will be centimeter. So let me show you my work. I have done this, and I will show you how this is done. Okay, so the D value was 4.7 centimeter on the map. If something is 1, in actual it will be 10. So if something is 4.7 centimeter, how much it will be in the actual? This is the proportion method which I'm using to find out the actual height of that clamp. So 1 by 4.7 will be equals to 10 by 3. So if you cross multiply, you get x equals to 4.7 multiplied 10. That will be 47 centimeter. So this is how you do this A part. And let's go to the next part. Okay, so the next part coming up on your screen. She adjusts the length of the thread until the height h of the center of the bob above the bench is 15 centimeter. She gives the ball a small sideways displacement and releases it so that it oscillates. She records the time for 20 oscillations in the table, figure 1.2. She repeats the procedure for height h equals to 20 centimeter, 25 centimeter, 30 centimeter, and 40 centimeter. She uses her results to calculate the period T for one oscillation and T square for each set of rings. Complete the table 1.2. Okay, so we have to complete this table. Now you can see here in this table, this is the height of that clamp above the bench, and this is the time for 20 oscillations. So she swings that pendulum, and she note how much time it takes for 20 swings. For example, in this first row, for 20 oscillations, the pendulum has taken 22.8 seconds. So this T means the time taken for one oscillation. You can find it easily. You just divide that 22.8 with the 20. That will give you the time period for one swing. Then you have to, whatever the time period you get, you have to square it. So let me show you. I've done this on a paper. So here we go. So when you divide 22.8 with 20, you get the time period for one oscillation, and that will be 1.14 second. And then you have to find the t square. So 1.14 square, and that will be 1.30. So this is how you will do this. This is 1 mark question. This is B part of the question number 1. Okay, so then they say she uses her results to calculate. Okay, so we are done with this. The second part is explain why measuring the time for 20 oscillations rather than one oscillation gives a more accurate value for the t. You see, whenever we find out the time period, we measure the time period for oscillations of a pendulum. We never directly measure the time period for one oscillation. We do not directly measure the time period for one oscillation. The reason is that you have to start the stopwatch, you have to stop the stopwatch. And you know, the humans, they have some reaction time. And because the time for one oscillation is very small, and the reaction time will have a large effect on that measurement. So what we do, we take 20 oscillations, we time 20 oscillations, we note down what is the time taken for 20 oscillations. Then that time is large. For obviously for 20 oscillations, the time will be large. So the effect of the reaction time of the human, that effect reduces. So the value which is calculated, and that becomes the effect on it of the reaction time becomes smaller. So that is the reason why we take the time for 20 oscillations instead of directly taking the time for one oscillation. It's a 1 mark question, but the answer is a bit technical. So let me show you my answer. I have tried to write this answer. When we time 20 oscillations, effect of reaction time on time measurement reduces. So let's hopefully you understand. So question number 1, and it's C part, and the first portion, he says on the figure 1.3, plot a graph of t square on the y-axis against h centimeter on the x-axis. Start your axis from the origin and draw the straight line of the best fit. Okay, so here you have that grid, and I have reduced the size. So this is the basic question. And they want you to draw the graph. And on the x-axis, we will take h, which is in centimeters. And on the y-axis, I will take t square, whose unit is second square. So, and this is that table. This is that table, and this h will be on the x-axis, and this is going from 15 to 40, and the t square, and we will plot that graph. So let me show you my work. I have done this. So, okay. So here you can see I have hopefully this is clear to you. H is on the x-axis. I've taken 10, 20, 30, and 40. So here I have taken 0 0.1, 0 0.2, 0 0.3, 0 0.4, 0 0.5, 0 0.6, 0 0.7, 0 0.8, 0 0.9, 1, 1.1, 1.2, 1.3, 1.4, 1.5, 1.6, 1.7, 1.8, 1.9. And then I will plot, this is that table, these H values 15, 1.30, 20, 1.08, 25, 0.88, 30, 0.69, 40, 0.28. So I have plotted those points here. This point is not the right point. So these are the dots, and then I have drawn here the line of best fit. Okay, so this is the line of best fit. So This is that question. Hopefully you can do that. And so it's how much marks? It has 4 marks. So then it says extend your line so that it cuts the y-axis. State the value of the intercept C on the y-axis. And then it says calculate the gradient M of your line, show your working and indicate on your graph the values you use to calculate the gradient. Okay, so let me show you. And this is that the y-intercept will be this. And this point is 1.8. And then it is, I think, 1.87. So the y-intercept is 1.87. So 1.87 is the y-intercept. So 1.87, this is the y-intercept. When the graph cuts the y-axis, that's the y-intercept. It is represented with the C here. It is 1.87. Then he says, calculate the gradient M of your line, show your working and indicate on your graph the values you use to calculate the gradient. So here you can see I have taken this point. This point is 10, 1.47, and I have taken this value, this point basically on this straight line, the line of best fit, 35, 0.5, and I will find the gradient. You know, the finding the gradient of a line, you remember in mathematics you have studied, the gradient is y2 minus y1 divided by x2 minus x1. So it will be 0.5 minus 1.47 divided by 35 minus 10, and that will be minus 0.97 divided by 25. So it will be minus 0.0388, which if you round it off up to and 100th, so it will be minus 0.04. So the gradient is minus 0.04. Hopefully you understand. Then they ask that theory suggests that H is given by the equation C by M. Use this equation to calculate H. So D part and the E part. Okay, so let's go to, and let me show you my work. I've done this. He says that the theory says that H will be equals to C by M. We have the value of the C and we have the value of the H. So 1.87 divided by 0.04, and that will be 46.75. So 46.8 centimeter. So compare your measured value for the H from the A second part. You know, when we measured the value of the H in A second part, that value was 47. And with your result in the D part, state whether the two values agree with each other and justify your answer. In the A second part, the H value was 47, and this value, which we just calculated by C divided by M, that is 46.8. So these values are very close to each other. So they agree with each other. Measured value is 47 centimeter. Calculated value is 46.8 centimeter. Yes, both values agree with each other. So we are done with the question number 1. So let me show you the marking scheme of this question number 1. And here we go. Question number 1, the marking scheme is showing up on your screen. You can do one good thing, that you can pause the video, take your time, read this marking carefully, read the marking scheme for each question, each number, that what you have to write. I have already checked my answers with the marking scheme, so they are good. You can also check your answers. You can check my answers as well. And whenever you solve a paper, whenever you do a question, always check your answers, match them with the marking scheme. It's very, very important. Okay, so let's go to the next question. The next question is question number 2. And he says, okay, a student investigates the effect of insulation on the rate of cooling of hot water in a beaker. He pours 250 centimeter cube of hot water into a beaker and places a thermometer in the water as shown in the figure 2.1. So here you have a beaker, this is hot water, and here you have a thermometer, and you are holding the thermometer with the help of a clamp, which is being supported by a retort stand. He waits for a short time. He then starts a stopwatch as he records the temperature theta of the hot water. This is at the time t equals to 0. So after some time, he note down what's the temperature and he starts the stopwatch, and the time he supposes is 0, and the temperature, whatever the temperature, he note down. Figure 2.2 shows the thermometer at the t equals to 0. Read the thermometer and record the temperature theta. And if I will increase the size so you can see it more clearly. So the reading is here. So this reading is, I think, 80, 86, 87, 88, 88 degrees centigrade. So the temperature is 88 degree. So you can write here 88 degree. Then he says, explain why the student waits a short time before recording the temperature of the water at t equals to 0. You see, when you have poured hot water into this beaker, you do not immediately start your stopwatch and note down the temperature, because you allow some time. You allow enough time that the thermometer starts showing the maximum temperature. So it takes some time. So you wait for some time so that the thermometer starts showing the temperature of the hot water, because thermometer will take some time to respond to that hot water. So let me show you my answer, and here we go. So the reading on the thermometer is 88 degrees centigrade. Explain why the student waits a short time before recording the temperature of the water at t equals 0. Allow thermometer to show the reading of the temperature of the hot water. You do not start immediately the stopwatch. You let you give it some seconds so that the thermometer shows the temperature of the hot water. Okay. So the next question and the next part coming up on your screen is, he says, the student records the temperature of the water in the beaker after 3 minutes. So after every 3 minutes, he notes down what is the temperature. He then pours the 250 centimeter cube of hot water into an identical beaker that is insulated with the cotton wool as shown in the figure 2.3. He repeats the procedure. Now he poured more 250 centimeter cube, another 250 centimeter cube of hot water into another beaker, but this beaker has a cotton wrapped around it. So you have put insulation around that beaker. So, and same, you have a thermometer in it. His results are shown in the figure 2.4. Complete the column headings in the table figure 2.4. So here the time must be taken in seconds. These are seconds, 3 minutes, 180, because he took the reading after 3 minutes, here 180 is written. So here you will write seconds, second. So temperature theta, that is in degrees centigrade, temperature theta, that is in degrees centigrade. So this is how you will fill it. So at the 0, the temperature is 88. Here you write 88. Then he says, add your values in the theta in the A first part to the table in the figure 2.4. Then he says, state whether the insulation has any significant effect on the rate of cooling in the first 3 minutes. Justify your answer by reference to the results. Okay, so let me show you my answer there, and from there we will justify our answer. Okay, so here you will write seconds, here you write degree centigrade, here you write degree centigrade, 88 here. So without insulation, that starting temperature is 88 degrees centigrade, and after 3 minutes the temperature has dropped to 75. So here we have a drop of 13 degrees centigrade, a temperature drop of 13 degrees centigrade. Here, when you have insulation around the beaker, the initial temperature of the water is 85 degrees centigrade, and after 3 minutes the temperature is 75. So there, here we have a drop of 10 degrees centigrade. So, and then their question is, state whether the insulation has any significance. You see, yes, insulation reduces rate of the cooling, and justification is without insulation temperature drop is 13 degrees centigrade in 3 minutes, and with insulation the temperature drop is 10 degrees centigrade. So you can see there is a slight reduction in the temperature drop. So yes, insulation has effect on the rate of cooling. So that is question number 2. I think question number 2 we are done with the question number 2. No, so no, C part we have. Initially, the main cause of the heat loss from the beaker is evaporation. Suggest how the student can reduce the heat lost by evaporation. If you want to reduce the heat lost by evaporation, the method is very simple because the evaporation takes place from the surface of the liquid. So you can put the lid, you can take a lid, a cap, and you can put it on the beaker. So when you put a lid on the beaker, it will reduce the heat loss by the evaporation. Then he says state one other modification to the apparatus in the figure 2.3 that reduces further the loss of the heat. So another thing which we can do is we can put something, a lagging, a mat under the beaker, because the beaker is also losing heat to the floor. So what you can do, you can, or the bench or the table, so you can put some insulation under the beaker. That will also reduce the heat loss. Then he says state one quantity that is kept constant to make a fair comparison between the rate of cooling of the two beakers. The few things which should be kept in both the beakers, and the initial temperature of the water in both the beakers should be same. The volume of the water in both the beakers should be same. The room temperature in both the experiments should be same. You only have to write one thing which should be same. So that is the D part. So let and then we are done with the question number 2. So let me show you my answer. So here we go. So how the student can reduce the heat loss by evaporation? Use a lid on the beaker. State one other modification to apparatus that reduces the further the loss of heat. Put lagging under the beaker. And state one quantity that is kept constant to make a fair comparison between the rate of cooling of the two beakers. Room temperature should be same for both the beakers. So this is question number 2. We are done with the question number 2. Let me show you the marking scheme of the question number 2. So here we go. So my dear students, the marking scheme of the question number 2 is showing up on your screen. You can pause the video and take your time, read each answer carefully, check each mark that what you have to write and what you cannot write. And I always tell you that checking the marking scheme is a very good habit. We always solve those questions whose marking schemes we have, and we always check our answers. We compare them with the marking scheme. Okay, so let's go to the next question. The next question coming up on your screen is question number 3. He says, a student measures the refractive index of the material of a transparent block ABCD by tracing the path of a ray of light through it. The experiment is set up as shown in the figure 3.1. So this is that experiment. So here we have a ray box which has a torch in it. So a light ray is incident on the AB face of this transparent block, and we have traced this block on paper. And let's. So here we have two dots. Here the emergent ray will be figure 3.1. He says, she directs a ray of light PQ from the ray box onto the side AB of the block. On the figure 3.1, draw normal to the side AB at the point Q. Extend the normal so that it crosses the side CD. Label the point at which the normal crosses the CD with the letter R. Okay, so let me show you. I have done this. Okay. So first of all, I have to draw the normal. So you can see that at the point of incidence, I have put the crosshair of the protector, and the zeros of the protector, they are on the AB line, and I have put a dot on the 90. Here you can see I put a dot here on the 90. And then I will draw this red line. This red line is basically representing the normal. So this is the normal, and you can see when this normal, I extended this normal, when this cut the CD side, I have labeled it as R. Okay, so that's the next part. Okay, so let me read the next part. Then he says measure the angle of incidence alpha of the ray PQ on the side AB. So we have to measure the angle of incidence. Let me show you. So if you want to measure the angle of incidence, you can see here, this is the zero on the normal, and this is the incident ray. So how much is the angle between them? 10, 20, and 30, something like 31. Okay, so I've written here 31. Hopefully you understand. This is how you measure the angle of incidence. Then their question is, she marks with crosses 2 points on the emergent ray from the CD as shown in the figure 3.1. On the figure 3.1, draw a line joining the two crosses and continue this line until it meets the QR. Label the point where the line crosses the CD with the letter S and the point where it crosses the QR with the letter T. Okay, so let me show you how this is done. So here are those crosses, and I will join them, and I will prolong that line until it crosses the normal. When it crosses the normal, I will name that point as T, and where it crosses the CD face, I named it as S. Hopefully you understand. Okay, so the next thing they are asking is, draw a straight line from Q to S. Then he says measure the length X of the QS. We have to measure the QS and the length ST. QS and ST. Okay, we have to measure QS and ST. We have to measure QS and ST. So measure this length ST and the QS. Okay, so here you can see I have joined the Q with the S and the T with the S, and I have measured them, and that is 5.3. This one, the QS is, which is represented with X here, is 5.3 centimeter, and the ST, which is represented with the Y here, that is 3.6 centimeter. So then he says the refractive index of the N of the material of the block is given by the equation N is equals to X by Y. So to calculate the N, so we have the value of the X, we have the value of the Y. I can calculate the value of the refractive index. So that's the question number. That's the question number 3. Okay, so here we go. So the N value is X by Y. The X is 5.3 and the Y is 3.6. So 5.3 divided by 3.6, and that will give you N value 1.47. And when you round it off, it will be 1.5. So the refractive index of that glass is 1.47. And when I round it off, it is 1.5. So that's question number 3. And let's check the marking scheme of question number 3. The question number 3 marking scheme is coming up on your screen. So my dear students, question number 3, its marking scheme is showing up on your screen. You can pause the video and take your time, read this marking scheme very carefully, check my answers, your teacher's answers, the answers given in the red spot with this marking scheme. It's very, very important to always check the answers, compare them with the marking scheme. Okay, so let's go to the next question. The next question is question number 4. He says a student investigates how the resistance of a wire depends upon its length. He uses the equation resistance is equals to the potential difference V divided by current I. The following apparatus is available. We have power supply, we have ammeter, we have voltmeter, we have switch, we have connecting leads and crocodile clips, a length of resistance wire, meter rule, wire cutters. With the plan for the investigation, draw a circuit diagram in the space below. Okay, so let me show you. I have done this. Okay, so here you can see I have drawn a circuit diagram. Here is the battery or the power supply. Here we have here you will have a switch, and here you have an ammeter, and here you can see I put a voltmeter which is parallel to the wire. These are the crocodile clips, and I have shown here a ruler to measure the exact length of the wire which is being used. And okay, so here you can see I have drawn the switch. Actually, in the last diagram, I've not drawn the switch. So here you can see I've drawn the switch. So hopefully you understand that what this figure represents. Okay, so let's move to the next part. He says, explain briefly how the student carries out the investigation. Okay, so let me explain to you. How do we? So I take a certain length of the wire, I put it beside a ruler, and I measure how much is its length. I put the crocodile clips here, and I check how much length of the wire is in the circuit. And then I close the switch. I note down what is the reading on the ammeter. Then I note down what is the reading on the voltmeter. And then I can divide the reading of the voltmeter with the reading of the ammeter, and that will give me the resistance of the wire. So let me show you. He says, measure the maximum length of wire and attach crocodile clips on its ends, switch on battery, and note voltmeter reading and ammeter reading. Cut wire into smaller piece and do the same procedure with shorter wire. Resistance of the wire can be calculated with R is equals to V by I. The next question is, explain how the student can use the readings to reach a conclusion. So how you can reach the conclusion? You will note down the length of the wire and its resistance, and you will observe that as the length becomes length is longer, the resistance is larger, and when the length is shorter, the resistance is smaller. Okay, compare resistance of different length of wires. Longer wires will have higher resistance. So that was the question number 4, and it's a C part. Hopefully you understand. Okay, so we are done with this. Okay, so that was a 1 mark question, and we are done with this paper. So my dear students, today we have done October, November 2017 and 4-2 paper. The marking scheme of the question number 4 is showing up on your screen. That's the question number 4. Let me reduce the size. Okay, so what you can do, you can pause the video and take your time and read this marking scheme for the question number 4 carefully, and you can see that it's very important to always check your answers and compare your answers with the marking schemes issued by the University of the Cambridge. Okay, so thank you very much. Today we have done that paper. This is October, November 2017, and paper. This is October, November 17, Physics 5054, paper 4-2. And hopefully you understand this paper, and I have tried to explain the concepts and the procedures in this. So thank you very much, everybody, for watching this video. I want to specially thanks the students who are watching my videos in Bangladesh, in Pakistan, in Bangladesh, in India, in Sri Lanka, in Mauritius, in Brunei, in UAE, in Saudi Arabia, and many other countries. So thank you very much, everybody, because when you watch my videos, it gives me energy. I will ask you, if this video is helpful to you, if you think that this video can help you, your friends, your class fellows, do share the link of this video onto your Facebook and into your Instagram account and Twitter accounts. And this will help me promote my channel. So once again, thank you very much, everybody. Have a good day, and God bless you all.